All right, I had a student email me to tell me that I had forgotten to do this one, and I certainly did because it had come detached and was not detached, but it was out of order and buried under something. So here we go. 1.5 kilogram physics book and setup shown connected to a 0.70, well, 750 grams, which is 0.075 kilograms. Book is given a push up the slope and released with a speed of 3.5 meters per second. Coefficients of friction are this and this. Draw a force diagram for each object. Alright, so I guess I'll do the cup first here. It's going to have a force of tension, and it's going to have force of gravity. Now I know that the force of gravity is going to have to be bigger than the force of tension because the acceleration is going to be down the ramp. There are no forces pushing this thing up the ramp. So the net force in this system is going to be down the ramp. Alright, so then the book, alright, it's moving up the ramp, so the force of friction's down the ramp. Force of gravity is straight down. Normal force is perpendicular to the ramp. Uh-oh, that was a poor normal force vector. And then force of tension is also down the ramp. And this is the angle of the ramp, theta. There's no force pushing up. The acceleration is going to be down the ramp. All right, acceleration of the system. All right, now I certainly recommend doing the Blob method here. We could do Newton's second law for each object. I will do that, I suppose, and do it the long way, but you could also do the Blob method. I guess I'll show both ways. So first of all, we know that this one's accelerating down. We know that this one's accelerating that way. So I'll do this object first. So mass of the cup, G, minus the force of tension equals mass of the cup times A. And it's only the y direction for the cup. Now, for the book, okay, we're going to have x direction and y direction. So in the x direction, we're going to have force of tension plus mu times Fn. Now, Fn is just going to be equal to Fg sine theta, so that's going to be mass of the book times g times sine of theta. That is the coefficient of kinetic friction because it's sliding. Equals mass of the book times acceleration. Now the y direction for the book, so this is the, I guess I should separate these two maybe. We've got the cup, these are the book. The y direction for the book is simply Fn. Oh, one thing, I made that the positive direction, right? Positive, positive, so is these two pulling in a positive direction. There is no force of momentum or anything like that. That's all there is what you see there. So in the y direction, Fn minus, oh, I forgot a force here. Oh, what a jabroni. All right. I forgot, my son just took a spill over there. You all right, buddy? All right. I forgot the x component of gravity here. Right, pulling it down the ramp. Y component there, so I realized it over here. So we're also going to have plus mbg sine theta. This should have been cos here. Wow, Harmon, you're making all kinds of mistakes here. So fgx equals mbg sine theta, fgy equals mbg cos theta, because the y component is the adjacent. So I forgot a force in the x direction of the book. Not good. Alright, so Fn minus mbg cos theta equals 0. And basically that's where I got the Fn to put in to the force of friction equation. Alright, so we use that one. So really this is what we're dealing with here. So I guess from over here I could say force of tension force of tension, bring the force of tension over here. The mass of the cup G minus mass of the cup A. So I brought that over to switch these two. Over here I'm going to have force of tension equals mass of the book A minus mu sub K, mass of the book G cos theta minus mass of the book G sine theta. Alright. And then we're, either putting this in for the force of tension or setting them equal to each other. Either way ends up being about the same amount of algebra, which is kind of terrible. But I'll follow it through here. So I'm going to say, well, I guess I'll put in for Ft, set them equal to, however you want to do it. It's all the same thing, really. Fc mass of the cup times G minus mass of the cup times A. This is a point where you probably just want to go ahead and put in some numbers here, but I'll do it out one more minute. One more line with the variables. Alright, and we're solving this for A. Alright. Very ugly. But we'll get there. So I'm going to bring the A's together. I'm going to bring this over to here, all of this over to there, and we'll see where we end up. Alright, so MBA plus MCA equals, so I'm bringing this over here, but then bring them over to the right. I'm bringing these over to here, and just switching sides. So MCG plus mu sub K MBG cos theta plus MBG sine theta. Great. You get A equals mass of the cup times G plus mu sub K times mass of the BG cos theta plus MBG sine theta divided by MB plus MC. Now, got to put numbers in. A equals mass of the cup times G. Cup is 0.75, so that's 7.5 plus 0.30 times mass of the book times G. It's 1.5, so it's 15 times the cos of 20 degrees plus mass of the book 15 newtons times the sine of 20 degrees. Alright, all divided by the total mass, which is 0.75 plus 1.5, so it's 2.25 kilograms. It's really the total force. Again, this is where you get to the Blob method. Right, you get to this step in the Blob method right off the bat. And I'll show you that in a second here. So we plug it on into our calculator, we get 7.5 plus 0.30 times 15 times cos of 20 plus 15 times the sine of 20. Alright, divided by 2.25. Acceleration equals 7.5 meters per second squared. It's, this is a case where you might be able to end up with an acceleration greater than g, right? Because you have a force pulling it backwards and you have a frictional force pulling it backwards. So anyway, interesting thing. But let me just go determine the tension connecting the book and the cup. Alright, so connecting the book and the cup, I just pick one of these equations up here and find the force of tension. So I'll just use this one here. Ft equals mass of the cup times G minus mass of the cup times A. Force of tension has to equal, well, I guess no, the A would have to be less than G so that this force comes out to be right. Yeah, definitely has to be less than G still. Very interesting. Anyway, force of tension mass of the cup here, 0.75 times G, so 7.5 minus 0.75 times 7.5. All right, so 7.5 minus 0.75 times 7.5. It's about force of tension of about 1.6 newtons or so. Let me just show you down here in this corner the blob method, okay? All right, so I treat it as, you know, we've got the cup and the blob, so it's 0.75 kilograms plus the 1.5 kilograms. Then we look at the external forces. So the tension's not going to even be factored in here. It's going to be, we're going to have force of gravity on the cup, right? And then we're also going to have force of gravity X on the book and the force of friction on the book, all acting to slow this thing down. So acceleration of the system equals F net over M. Well, F net here, so force of gravity on the cup is mass of the cup times G. Force of gravity X on the book is the X component here, right? I almost missed that one. That would have been a big error. So X component of gravity in the book is FG mg times the sine of theta. M book G sine theta. And then the friction down the ramp is the coefficient of kinetic friction times the normal force. The normal force, again, right? Normal force, again, has to be equal to FGY, which is M mass of the book times G times the Y component is cos theta all over mass of the book plus mass of the cup. And that is identical to this equation here. We would have gotten there in one step. But it's good to show the proof once in a while just to see it now. Hopefully I plugged everything right in here, got the right number. Somebody will probably email me if I didn't though. All right, have a good one.